Hey everyone, welcome to University of Winnipeg Chemistry 11-12. Dr. Carroll here. We're looking at the third lecture on the electrochemistry chapter, chapter 17. Today it's about free energy and electrochemistry. This is a topic you did not get to in grade 12. It's a pure university topic. Isn't that exciting? It begins on page 857. We've looked at delta G before. If delta G is less than 0, it's spontaneous. And we also know that if the cell voltage is greater than 0, it's spontaneous. Can we link the two together? The answer is yes. And we need a constant to help us determine that. And the constant is called the Faraday constant. It links chemical amounts in moles and electrical amounts in coulombs. So you'd always be given the Faraday constant, named after Michael Faraday. It's 96,485 coulombs per mole. Okay, so that's the link between electrical charge and moles. And putting them together, we get this expression for free energy. Delta G is minus N, so that's the number of moles that are transferred. So usually 1, 2, 3, 4, 5, 6. Rarely is it more than that. F is the Faraday's constant, and E is the cell voltage. So if you're talking about units, if N is moles, F is coulombs per mole, and E is joules. A joule is a volt, let's get this right. Volts. 1 volt is 1 joule per coulomb. So the coulombs cancel, the moles cancel, and you get units of joules. So the units do work out. And if we're talking about standard states, then delta G naught is minus NF times E naught. And N is really the least common multiple of the oxidation half reaction and the reduction half reaction. So let's look at this example here. We have a galvanic cell constructed from a silver chloride, silver electrode in contact with a solution containing chlorides and iron electrode. Okay, and we have silver chloride is gobbling up an electron, and a chloride is released. So this one's a bit more advanced than some of the ones we've looked at. The iron 3 plus gobbles up 3 electrons. So my N equals 3. My E naught for this reaction is 0.2223 minus a minus, so 0.25 something, 0.259 joules per coulomb. So the bigger that is, the bigger negative value of delta G naught it'll be, and the more spontaneous it will be. So delta G naught is minus 3 because you're transferring 3 electrons times Faraday constant, 9.6485 by 10 to the 4 coulombs per mole, times the, what the heck is this? This is my cell voltage, 0.259 joules per coulomb, and you get minus 75 kilojoules per mole when you convert to kilojoules per mole. I'm seeing, why do they have Cl minus in the iron? Am I going to be using that for anything? No, maybe later on if they go back to that. Okay, so that's one equation. There it is. Delta G naught is minus NF E naught. We also remember that from chapter 14, a long time ago, delta G naught is minus RT ln of KEQ. So you can put those together, right? If two things both equal the same thing, then they equal each other. So solve for E naught. E naught is RT over NF natural log of KEQ. So look at this. The greater the equilibrium constant, the greater will be the standard cell voltage. N is how many? Is our least common multiple when we're looking at the OHR and the RHR. F is a constant, R is a constant. T is the temperature. Now typically we look at 298.15 Kelvin. We don't have to. We can look at another temperature if we want. But if we look at 298.15 and we want to use log to the base 10, which is still considered easier to use than natural log. I don't know why. I think it's back to the days of logarithm tables that were used in CRC handbooks. Those same tables that my grandfather used to make. So in homage for my grandfather, we'll use the log here. Though you'll see some with the natural log as well. So E naught is 0.0592 over n log of KEQ. So, and the R I use is 8.314. Now, if we try it natural log, I think I take the 0.0592 and divide by 2.303, and I get 0.0257. That's right. So you can also write it as 0.0257 over n natural log of KEQ. Okay, so that's another way that you can express the cell voltage as a function of the natural log of the equilibrium constant at room temperature, 298.15 Kelvin. Okay, so let's try example 1712 here on page 859. Here we have a shorthand notation. We're going to get E naught cell, then we're going to get KEQ. Let's also get delta G naught. Let's put that in. It wasn't asked for, but let's push the limit a bit here. Standard conditions, I'm going to assume 298.15 Kelvin. So the copper is going to be oxidized and the bromine is going to be reduced. Bromine's higher up in my entries. These are the various entries in my SRP table. So the voltage then is 0.724 volts. It's going to be spontaneous, and bromine, bromide are on the same couple there. I wonder why it says bromide liquid. Let's take a look at that for a second. Is that the one that's right around the, yeah, okay, there's bromide liquid, good. I'm going to put a bookmark on page 853 since I use that so much. So E naught is positive, 0.724, and then I want to take my N here is 2. This common multiple of 2 and 2 is 2. So log of KEQ is 2 times 0.724 over 0.0592, 24.5, and the inverse log is 3 by 10 to 24. So we're saying that, wow, this reaction happens nicely, very product favored, very spontaneous. Essentially, the redox reaction goes to completion. Bromine is a potent oxidizing agent, and copper is relatively easy to oxidize. If I want to get delta G naught, it's minus RT ln of KEQ. So minus 8.314 times 298 times the natural log of this big number here. What is that? 3 by 10 to the 24. Okay, the question didn't ask for this, but I'm putting it in anyways. So 8.314 negative times 298 times 3 by 10 to the 24 natural log minus 1.40 by 10 to the 5 joules. Okay, and sometimes they like these because they're big in kilojoules, minus 140 kilojoules approximately. Okay, let's get the equilibrium constant for this one. So we see that the lead is oxidized and the tin is reduced. So E naught cell, so we have the two couples. So we got a tin 2 plus and not a rin tin, and the other one. So let's get to the which one's tin 2 plus is going to be minus 0.137, and the lead 2 plus is just above it, minus 0.126. The thing is, though, that they're demanding that the tin is reduced. So my cathode is demanded to be minus 0.137. So E naught of cell is minus 0.137 minus, you're demanding that the lead is oxidized. So minus 0.126. See, it doesn't want to go this way. This is a non-spontaneous process, but you're asking, hey, for this reaction, what's going on? So 0.137 minus plus 0.126 is minus 0.011. So this is a non-spontaneous process. It's not galvanic. The reverse process would be spontaneous, but that's not what it's asking for. So the equilibrium constant, KEQ, is 10 to the n. Now my n value is 2. My E naught is minus 0.011 over log of KQ is n E naught over 0.0592. 0.0592. So 2 times 0.011 negative divided by 0.0592, and I take the inverse log to the base 10, 0.42. Is that what the book says? 0.43, 0.425, fine, close enough. 0.42. So you see that this process really doesn't happen in any great amount. So 0.42. Okay. Now my pen got stuck. Let me just try to refresh here. That sometimes work. Let me go into draw. Oh, yeah, back again. Oh, I saved the day there, huh? I'm impressed. Okay. Now, let's get back to the page I want it to be on. Good. Okay. So, and you could get delta G naught now that you know your value of K. So, it's going to be, well, it would be a positive value, right? KEQ is 0.43, so delta G naught is minus R. That's too thick, isn't it? 8.314 times 298 times the natural log of 0.43, right? Which is going to be a positive value. So 8.314 negative times 298 times 0.43 natural log 2.1 by 10 to the 3. Okay, so it's non-spontaneous in the forward direction. Now, we've been looking at standard conditions, but you can make electrochemical reactions that aren't spontaneous into spontaneous reaction by fiddling around with the pressures and concentrations and going non-standard. And that's what the Nernst equation is all about here. You can also play around with the temperatures. So we proved the Nernst equation. We recall that delta G is delta G naught plus RT ln of Q from equation 1213 way back in this course. And we now know that delta G is minus NFE. Delta G naught is minus NFE naught. So plug those in. And then divide both sides by minus NF, and you end up with E equals E naught minus RT over NF, ln of Q. So that is the Nernst equation. If you're at 298.15 Kelvin, you get E equals E naught minus 0.0592 over N log of Q, Q being the reaction quotient, which we are now very familiar with. So this is one way to represent the Nernst equation. You could also write it as E equals E naught minus, okay, what do we do again? How did we remember to do that again? We were going to divide by 2.303 to get 2.303. So 0.0592 divided by 2.303, which takes you between log and natural log. 0.0592 divided by 2.303, 0.0257. Okay. So let's see how the Nernst equation works. I'll use log to the base 10 because that's what the book does. The permanganate ion is a powerful oxidizing agent that oxidizes water to oxygen under standard conditions. The shorthand notation, here it is. So there's oxygen and H3O plus there. Then we have a salt bridge, MnO4 minus, H3O plus, Mn2 plus. So what's the potential of a permanganate oxygen cell operating 25 degrees Celsius, pH of 7, so that we know that H plus concentration isn't 1 molar, it's 1 by 10 to the minus 7 molar. Oxygen partial pressure isn't 1 bar, it's 0.2 bar. MnO4 minus is 0.1 molar, and Mn2 plus is 0.1. So there isn't anything standard about this, but we can still get what's going on. So this is a quantitative problem. Yeah, there's lots of numbers. The problem's asked about an actual potential under non-standard condition. I call it voltage. I don't think you should call it a potential. We must visualize the cell, determine the balanced reaction. Half reactions are deduced from the shorthand notation. So MnO4 minus is the manganese is being reduced, and there's my E naught from data in Appendix F. Oxygen 0 here, minus 2. So if manganese is reduced, something has to be oxidized here. Well, this is 0. This is minus 2, so this is reduced. So how can they both be reduced? Something seems odd here. Are we missing something in here? Let's see. 6, 12, 12. Oh, the oxygen here in H3O plus is minus 2. Here it's minus 2. Here it's 0. Here it's minus 2. So that appears to be reduced. Oh, so the manganese has got to be the other. Minus 2 plus 3. Well, oh, okay, it's going here. It oxidizes water to oxygen, so I'm going the wrong way. You go water to oxygen, so it's going from minus 2 to 0. Yes, okay, so that's the oxidation. Okay, that just took a little while to figure out there. You just take the entry values though, 1.507 minus 1.229, so it's 0.278. When we're balancing it, these are both balanced. You flip this around, and then you got to find the lowest least common multiple of 5 and 4, which is 20. So you multiply all this by 4, all this by 5, and you got H2Os all over the place, but they cancel out partially, and you end up with 48 minus 30, 18 H2Os on the right. So here's my reaction. Balanced 4MnO4 minus plus 12H3O plus goes to 4Mn2 plus plus 5O2 plus 18H2O. And so the cell voltage in this non-standard is minus 0.0592 over n. So n's a big one here, isn't it? In this equation, sometimes they can get large. 20 log of Q. So Q is my Mn2 plus concentration, which is 0.1 to the fourth, times the partial pressure of O2, 0.2 to the fifth, don't worry about liquid water, divided by my MnO4 minus, which is 0.1 to the fourth, times H3O plus, which is 10 to the minus 7 to the 12th. Wow, to get the Q. Okay, so there it's all in all its glory there. Wow, that's a lot of powers, eh? Look at that, 3.2 by 10 to the 80th for Q. Log of Q is 80.505. Plug it in, and you get 0.04 volts. Okay, so our standard cell voltage was 0.278, and now we've decreased it to 0.04. So the low concentration of H2 plus in pure water reduces the cell potential nearly to zero, but the reaction is still spontaneous, right? E is still positive, so permanganate can oxidize water. Solutions of potassium permanganate slowly deteriorate and cannot be stored for long times, but you can keep them for a while. So, interesting question. Let's try 1713. Determine E for the reaction of lead with SN2 plus described in practice exercise 1712. Well, did I do that one? Yeah, I did. And so in 1712, we had PB plus SN2 plus goes to PB2 plus SN. And so my Q is PB2 plus. This is all balanced. That's all good, right? 4.75 by 10 to the minus 4 over SN2 plus, which is 0.255. That's self-balanced, right? So my Q is 4.75 by 10 to the minus 4 divided by 0.255, which is 1.86 by 10 to the minus 3. And my log of Q is negative 2.73. My E equals E naught. So E naught I did in practice exercise 1712, which I don't know if I still have that written out. Or is that when I refreshed the things there? Oh, delta G naught equals minus RT. Okay, well, fine. I'll just look at it again. It's no big deal. I want to take, let's go back to where we were. Okay, so I got to go back to the table. So the tin 2 plus and the lead 2 plus. So negative 0.126 and negative 0.137, and I want the tin 2 plus to be reduced. So it's negative 0.137 minus 0.126. So in other words, 0.137 negative plus 0.126 is negative 0.011. Negative 0.011. E equals E naught. Now what's my next equation? Minus 0.0592 over N. 0.011 minus 0.0592 over N. N is 2 here, right? 2 log of Q, which is minus 2.73. So 0.011 negative plus 0.0592 divided by 2 times 2.73 is 0.07 volts. Okay. Now, do you notice something here? It was negative. The standard cell voltage, also loosely called cell potential, is 0.07 volts. Sorry, is minus 0.011, saying that it's non-spontaneous. But if I make the lead ion small, like really small, then I've managed to shift the spontaneity so it is going to the right-hand side. Now, it's not quite Le Chatelier's principle, but it does remind me of it a little bit. But the idea here is that you can make something that would not spontaneously happen by choosing judiciously what concentrations of ions or what pressures of gases to put in to create your galvanic cell. And that's exactly what's done here. So we create a spontaneous galvanic cell by mucking around with the initial concentrations. And as you might gather, as time goes by, these concentrations change. This becomes a much more involved process. We're just looking at the initial steps associated with them. Okay. Example 1714 is shifting things about a bit. For this one here, we looked at it. We got the standard cell potential was 0.278 volts, this permanganate thing. And suppose the cell potential under non-standard conditions was 0.2. So E is 0.2. E naught, we got from our table, is 0.278. We want to get the partial pressure of oxygen. See, you have this and this, 0.0592 over well, they put it all there. They're using natural log here, aren't they? Okay, that's fine. Why did they switch to natural log there? I would have kept it in log to the base 10 because the other ones were done that way. But now what else are we given? We're given the MnO4 minus, we're given the Mn2 plus. So you got to solve for the partial pressure of oxygen. So you end up going to take the fifth root of something, and you end up with 0.036 bar. So you figure that out, and you should get that value. Okay. And you can also try practice exercise 1714. pH meter uses the Nernst equation, and in so doing can get the concentration of H plus, runs it through a current, and you get a readout. Okay? So those are examples of the Nernst equation. I'm sure you'll find some in your Wiley Plus assignments. Okay, let's talk a bit about electrochemical stoichiometry. You can relate moles to change and Faraday's to chemical change in terms of electrons. Faraday's constant plays a role here. So does current. So we know that from physics that current is charge over time. In physics, we write Q over T, where Q stands for charge, not for heat. So Q equals IT, which means coulombs is amperes times seconds, right? An ampere is a coulomb per second. So there's IT, so what's that? So that's charge over Faraday's constant, which is in units of coulombs per mole, so you end up with moles. So moles of electrons, N, is current times time in seconds over Faraday's constant. And this is a useful equation, regardless whether we're talking about galvanic cells or electrolytic cells. So N is IT over F. Okay, so I never liked that question. I'm not going to bother with it. You know what? Fine. You want me to look at it for a second? Okay, I'll try one more time. So we have a automobile headlights typically draws 5.9 amps of current. Okay, so we're using a battery to get the headlights going. Galvanic cell is used in our car battery. Assume that the battery can supply 5.9 amps until all the lead oxides can be consumed. How long will it take for a battery to run down? If the lights are left on after the engine is turned off, so there's no recharging happening here. Okay, so 250 grams of lead oxide. I can get the molar mass of lead oxide to get the moles. And in my equation for the batteries, I see every mole of lead oxide is going to need 2 moles of electrons. Okay, so jumping to page 864. So the number of moles of lead oxide would be 1.05, so I need twice as much, 2.1 moles of electrons. And once I have 2.1 moles of electrons, I know the current drawn, I know Faraday's constant, I can solve for the time needed to make that happen. So the time needed is moles of electrons times Faraday's constant over the current. So 2.1 moles times 96,485 coulombs per mole times 5.9 coulombs per second. So that'd be how many seconds, and then they snuck in. I don't like when units are just snuck in there. Get the value in seconds, let's say, and how many hours would that correspond? That would be a better way of doing it, but they didn't do it that way. So anyways, 9.5 hours. So the maximum time the battery could supply current is 9.5 hours, but the voltage drops as the battery operates. And so it's actually going to stop keeping the headlights on less than 9.5 hours away. And you can try practice exercise 1715 on your own. So now we have a revisit of the how to get moles. Pure substance, moles is the mass over the molar mass. For solutes, the mole of solute is molarity, or concentration, times the volume in liters. And gases, moles of gas is PV over RT. We're talking about getting moles of electrons in electrochemical situations. It is the current times the time divided by Faraday's constant. Okay, section exercises you can do on your own, and don't worry about 17.53, that's just a mess. But these two you should be able to do, 17.51 and 17.52. Okay, I'm going to talk about the quantitative questions again in a minute or two. Redox in action, batteries, you can read about them. There's hardly ever any questions about batteries that are asked. But it's sort of cool. It's these pictures of them. Different kinds, primary batteries, secondary batteries, which are rechargeable, like a car battery. It's called a storage battery. Nickel cadmium batteries. We're still talking about them. They aren't used much anymore. Look at this. Cadmium is a toxic heavy metal. So sales are declining. Lithium ion batteries are being used more. Nickel metal hydride batteries can be used. So you can read that on your own about batteries. Corrosion, you actually get a mini electrochemical cell created when things start to corrode. Oxygen is key for corrosion. Rust is an example of corrosion. Corroding bridges, that's scary, right? So a little bit on corrosion, fuel cells if you're interested, some technology about that. That snuck in there. There's back to the corrosion, some rust there. See this little reaction happening, the eating away on an iron surface through this electrochemical process, which is corrosion, and you have to try to fight that. Okay, in the last little topic, electrolysis, we just get the general idea and then we do some number crunching. So in electrolysis, you are using electrical energy to make a chemical process happen that otherwise wouldn't. So you have to supply a external power supply of some kind to force things to go in directions that they wouldn't otherwise. And the process of using electrical current to drive a redox reaction that otherwise wouldn't go is called electrolysis. It's also used to talk about breaking things up by zapping electricity, like electrolysis of water, right? You run a current through water and you collect hydrogen and oxygen. That's our classic electrolysis process. Okay, so the external voltage supplied has to be of opposite sign to the non-spontaneous process as written left to right, and at least equal to or greater than, actually not equal to, it has to be greater than, so you can push electrons in the other direction. Okay, here we see the electrolysis of water, hydrogen and oxygen bubbling out. Here we have an example of electrolysis and stoichiometry. So if the electrolytic cell shown in figure 1723, okay, so what page is that on? Oh, that is the hydrogen and oxygen being collected. Draws a current of 0.775 amps for 45 minutes. So right off the bat, I want to find out how many electrons there are. Or you want to calculate the volume of hydrogen and oxygen, all gases at 1 bar. So let's find the moles of electrons that's associated. We're running a current of 0.775 amps. Amps is coulombs per second for 45 times 60 seconds divided by Coulomb's constant. So you get 0.0217 moles. Okay. Here's the processes. The amount of hydrogen gas formed. You have 2 moles of hydrogen for 4 moles of electrons. Reduce that to 1 to 2, I guess. 1.084 by 10 to the minus 2 moles of hydrogen. And for this half reaction, we're just having the half reaction so everything's cancel out nicely. Well, so the moles of electrons, 0.02169, that's the same. 1 mole of oxygen is associated with 4 moles of electrons, so 0.5423 by 10 to the minus 2 moles. We want to get the volumes, they're both gases, so we use PV equals nRT. Haven't used that in a while. So the volume of, we plug it in. It's not a stoichiometric calculation, it's just plugging in the moles, RT over P. So hydrogen is 0.265, and lo and behold, the oxygen is 0.133. Okay, so I'm going to show you a different example of this, which I think is more common. Let's say I'm going to call this cathodic reduction. I'm just going to make one up off the top of my head. Let's say you have some reaction. You got some anion going on too, but you got chromium 3 plus 3 electrons goes to chromium. And let's say you run a current for 3 minutes, 4 amp current. I want to find the mass of chromium formed. So this is a classic kind of question, and I'm sure there's some end of chapter questions which will help you on that. So 3 minutes, 4 amps. We want to get the mass of chromium formed. So this we have here that 3 moles of electrons for 1 mole of chromium. So at the cathode we get reduction, whether we're talking about a electrolytic cell or a galvanic cell. Cathode is the reduction. So here I have a cathodic reduction. The creation of 1 mole of chromium solid needs 3 moles of electrons. This could be aqueous. This could be solid. So what was that thing? What was it? N equals IT over F. Okay. So, I mean, there's some smoother ways to do it. I'd like to just do the different parts here, just to get a better feeling for what's going on. So the moles of electrons I actually deliver, it might not be 3. It might be different than that. Let's find out. So you're given that the 4 amps, and the time is 3 minutes. So I can do that in my head. That's 60, 120, 180 seconds. Faraday's constant, 96485. So 4 times 180. 4 times 180 divided by 96485. 7.46 by 10 to the minus 3 moles. Okay, so the amount of chromium would be a third of that, right? 7.46 by 10 to the minus 3 moles of electron, 1 mole of chromium for 3 moles of electron, divided by 3 is 2.49 by 10 to the minus 3 moles of chromium are formed, and the molar mass of chromium, I have no idea, I want to say it's 51.99, but it is, flipping here, chromium, it is 51.996, that's just sad that I know that off by heart, isn't it? 51.996 grams per mole. So 2.49 by 10 to the minus 3 times 51.996 is 0.129 grams chromium. Okay, so those are typical kinds of questions you'd find with electrolysis and quantitative electrolysis. Now, sometimes when you run currents through, you have battles going on because the water may want to split apart. And so sometimes you do things in aqueous solution, sometimes you do them in molten solution. And this is a bit more than what we do in the course, but there are I just want you to know that there are competing effects. Now we were talking about that example there. That example I just did on the paint program could be an example of plating a crappier piece of metal with a nicer piece of metal on the surface, right? Like not stainless steel, but silver plated, like silver plated cutlery. It's not as nice as sterling silver, which is silver all the way through and is like $4 billion, but silver plated at least has a coating of it. Stainless steel is good enough for me. Anyway, so you have electroplating and oh, actually we're going to do an example of that, aren't we? Here we go. Okay. We can coat some jewelry with gold. What mass of gold can be deposited from a solution that contains gold cyanide ions if the current flows 5 amps for 30 minutes? Okay, so this is similar to one I just did, right? So the moles of electrons is, you got the current 5 coulombs per second, 30 minutes, convert to seconds, divided by Faraday's constant. So I got 0.0933. Then I have this equation. I'm running electricity through this gold cyanide taken 4 times ion to get gold. So I need 3 moles of electrons to give me 1 thing of gold. Well, I got 0.0933, so a third of that is how many moles of gold are plated, and the mass is multiplied by the molar mass, 6.1. Now, an interesting thing to see here is if I run a greater current through there, I'm going to get more gold, or the same current for a longer amount of time. This number's bigger, so this number's bigger. So it makes sense. The longer I run the process for, the more gold is going to plate out on the base metal to make some pretty jewelry. Okay, and this silver one, you can do that one on your own. Sometimes you use electroplating to prevent corrosion of the metal underneath. It's called a sacrificial metal. And here we see chromium can plate steel. Zinc can plate steel. Steel being iron. And that process, you may have heard of it before, galvanization. So we talk about galvanized steel. It means you got zinc has the outer surface, and it is the zinc that is oxidized, protecting the iron underneath. And there's other examples. Ooh, that's pretty. Okay. And what do we have next? Oh, then we have our visual summary. So we decide how we can recognize something has a redox reaction or not. Our definitions, balancing redox reactions, galvanic cells, all about that, cell potentials. Then we got the equations for the Nernst equation, delta G naught, minus NFE naught, equilibrium equation, the equilibrium constant related to E naught, some practical examples of redox in everyday life, and some discussion about electrolysis. Sounds good? Have fun with all these questions.